1, 2, 3, 4. By the time I reach 10, the inside of a Formula One engine has reached a state of violent physical extremity. 5, 6, 7, 8, 9, and 10. This diagram maps a single piston stroke. In those 10 seconds, this cylinder fired 2,000 times. The internal temperature spiked to 2,600 degrees Celsius, and the downward pressure slamming into this single piece of metal equaled the weight of 4 adult elephants. Subject a standard commuter car engine to those forces at 15,000 revolutions per minute, and the metal block would simply melt into slack or shatter. Preventing that catastrophic failure requires scrapping the traditional automotive assembly line. These power units are built in aerospace-grade cleanrooms, where a single microscopic speck of dust between moving parts is treated as a critical threat. Surviving this environment forces engineers to rethink the physical shape and behavior of metal on a microscopic level. Take the piston itself. A single one costs over $66,000 to produce. If you measure it, you will find an intentional, highly calculated flaw. It is machined as an oval, not a perfect circle. This wireframe animation illustrates why. As the engine reaches its maximum heat and stress, the aluminum alloy undergoes severe thermal expansion. The oval is mathematically modeled to deform into a perfect circle only when exposed to peak operating temperatures. Predicting that expansion requires machining tolerances as tight as 10 microns, a fraction of a human hair's thickness. To maintain speed without catching, the piston relies on ultra-thin 0.7mm titanium rings and is coated in diamond-like carbon to strip away friction. Without that intentionally warped geometry and frictionless coating, the expanding metal would jam against the cylinder wall, seize up, and tear the engine apart from the inside. Containing these forces requires an immensely strong outer structure, the engine block, or the rib cage of the car. But traditional metal casting techniques cannot create the intricate internal cooling channels required to manage 2,600 degrees of heat. Manufacturers bypass this limitation using a process called sand printing. Robotic 3D printers build core molds layer by layer, utilizing slices of synthetic sand just 0.25 millimeters thick. During casting, liquid aluminum-lithium alloy is carefully pushed uphill into these molds, preventing air bubbles and eliminating structural weaknesses. By merging 3D printing with advanced metallurgy, teams yield a block that is light enough to carry with one hand, yet strong enough to house thousands of explosions every minute. Despite this mechanical precision, the 1.6-liter V6 internal combustion engine only generates roughly 600 to 700 horsepower on its own. This glowing schematic reveals the rest of the equation. To reach 1,000 horsepower, the car utilizes the NGUK, or Motor Generator Unit Kinetic. It captures wasted kinetic energy from the brakes, converting it into electricity. Simultaneously, the MGUH harvests extreme waste heat from the turbocharger's exhaust. All recovered energy is stored in a central lithium-ion battery, deploying an instant 160 horsepower boost directly to the drivetrain. A modern Formula One power unit operates as a closed-loop energy recovery ecosystem designed to waste absolutely nothing. Having achieved the most thermally efficient internal combustion engine on Earth, teams now extract maximum power, burning a strict limit of 110 kilograms of fuel per race. But the engineering target moves again in 2026. New regulations will force cars to run entirely on advanced sustainable fuels, completely eliminating crude oil. This graphic illustrates the chemical cycle. E-fuels are synthesized by capturing carbon dioxide from industrial waste. Chemists build the exact molecules needed. Because carbon was pulled from the air, burning it creates a net zero equation. Zero new carbon is added. Formula One functions as a 1,000 horsepower laboratory. The microscopic precision, the hybrid energy loops, and the sustainable chemistry proven on the track today are actively prototyping the vehicles we will drive tomorrow.